Hello everyone, my name is Vandana Singh and I will be presenting my project on star clusters with Gaia. The project was supervised by Dr. Priya Hassan. The main aim of the project was to determine distances and ages of various star clusters using Gaia data. Broadly, the methodology used was to first acquire the data, then identify the cluster members from the data, plot color magnitude diagrams for the cluster, and fit isochrones of different ages to the data to get the best fit and hence obtain the age and distance of the cluster. The tools I have used for this purpose are TopCat developed by Mark Taylor, Padova isochrones, and the preliminary use of a Jupyter notebook for initial plotting. Stars are born from giant molecular clouds and are thus formed in groups or clusters having a common origin. They are gravitationally bound to each other for some span of time. Stars in a cluster have the same age, chemical composition, and they are at the same distance from the Earth, differing from each other only in their masses. Hence, star clusters can be used to study and test models of stellar evolution. There are two types of star clusters. The open clusters, these are found in disks and spiral arms of galaxies. They are a loose collection of about 100 to 1,000 stars. They contain young stars and have an age ranging from 1,000,000 to 1,000,000,000 years. Globular clusters are found in the halos of galaxies. They are more compact and contain 100,000 to 1,000,000,000 stars. Globular clusters contain stars older than about 10 billion years. For this project, I have used data from the Gaia mission, in particular the early data release 3, which gives positions, parallaxes, and proper motions for a huge number of stars in the instrument magnitude range 6 to 21. The table gives the uncertainties in the astrometric parameters up to the instrument magnitude of 21. Using the methodology outlined earlier, I have analyzed 6 open clusters and 1 globular cluster. I will be explaining in detail the method I have used using the open cluster NGC 3293 in the constellation Carina. I acquired the data using a cone search of half-degree radius. Then I plotted proper motion in right ascension versus proper motion in declination. The non-cluster members in the field of view have random proper motions, so I selected the high-density regions shown in blue as my probable cluster. I plotted a histogram of parallax. The purple one refers to the probable cluster. As seen from the statistics, the parallax is 0.35 milliarcsecond, but its standard deviation is high, indicating that my probable cluster contains non-cluster members also. So I limited the range of parallax as shown, and now the standard deviation reduced to 5% of the parallax. I then plotted a color magnitude diagram as shown. This is a plot of apparent magnitude on the y-axis versus the color index on the x-axis. As mentioned earlier, the uncertainties in parallax for Gaia EDR3 are higher at higher magnitudes. This is shown in the next plot, which gives the uncertainties for a given data point at magnitude greater than 20. Therefore, I applied a photometric cut and eliminated stars of magnitudes greater than 18. This led to the green data points seen in the color magnitude diagram on the right. This shows a sky vector plot. The blue vectors depict the data after the photometric cut was applied. This data is now taken as the cluster. It is seen that all the stars in the cluster have the same direction of motion. A cube plot drawn for the cluster data shows that the stars are at the same distance from the Earth. So now I have a cluster which has a parallax of 0.39 plus minus 0.02 milliarc second at an approximate distance of 2564 plus minus 131 parsec. The next step is isochrone fitting. Isochrones are single-age models of stellar evolution. They are plotted on the color magnitude diagram as a trend line where the actual cluster data should lie. The age of the isochrone that gives the best fit to the cluster data is the best estimate of the age of the cluster. So I plotted different isochrones on my color magnitude diagram. One such isochrone of log age equal to 7.1 is shown with the cluster data. The two do not coincide as the cluster is plotted with apparent magnitude while isochrones are in absolute magnitude. The amount by which the cluster data has to be shifted along the y-axis so that it coincides with the selected isochrone is called the distance modulus. This shows the cluster after the y-axis shift. There now is an offset along the x-axis. This is due to interstellar extinction and reddening. The light from the cluster passes through interstellar dust before reaching the Earth. Absorption of the light by the dust grains causes dimming of the light received on Earth, a phenomenon called extinction. Due to their size, the dust grains also scatter blue light and allow red light to pass through, making distant stars appear redder than they already are. Thus, extinction and reddening corrections, as shown, have to be applied to get the corrected distance. This plot shows the color magnitude diagram with three different isochrones of log age 6.8, 7.2 and 7.4. The next plot shows that isochrones of log age between 7 and 7.1 would be the best fit to the cluster data. Hence, the age of the cluster NGC 3293 is found to be between 10 and 12.5 million years, and it is at a distance of 1,950 plus minus 131 parsec. Here I have used a Jupyter notebook to plot the color magnitude diagram of the cluster data and fit the isochrone of log age 7.1. I proceeded in a similar way to analyze the open cluster NGC 581 in the constellation Cassiopeia. This proper motion plot shows in blue the probable cluster that has been identified. After plotting a histogram of parallax, I did a parallax and photometric cut and obtained the color magnitude diagram as shown here. The lower plot shows the sky vector plot. The parallax obtained for this cluster was 0.35 plus minus 0.02 milliarc second at an approximate distance of 2824 plus minus 161 parsec. After isochrone fitting and applying extinction and reddening corrections, the corrected cluster distance was 1584 plus minus 161 parsec, and the age of the cluster was 25.1 million years. And for the open cluster NGC 6231 in the constellation Scorpius, this is my probable cluster. And these are the plots that I got. The cluster was found to have a distance of 743 plus minus 81 parsecs, and its age is 10 million years. For the open cluster NGC 6913 in the constellation Cygnus, the plots show the probable cluster, color magnitude diagrams, and statistics. For this cluster, the distance is found to be 1071 plus minus 91 parsecs, and its age is 3.9 million years. This is for the open cluster IC 1805 in the constellation Cassiopeia in the Perseus arm. The distance for this cluster is found to be 1563 plus minus 555 parsecs, and its age is 6.3 million years. And for the open cluster NGC 1960 in the constellation Auriga, I got a distance of 912 plus minus 28 parsecs and an age 25.1 million years. I also analyzed one globular cluster, that is M4, also known as NGC 6121, in the constellation Scorpius. It is interesting to note that the color magnitude diagram for this cluster is very different from that of an open cluster. Here, stars above the turnoff have evolved away from the main sequence, and other branches like the red giant branch, the asymptotic giant branch, and the horizontal branch have formed. These branches represent more advanced stages of stellar evolution. This shows the statistics for the cluster. In this plot, the isochrone of log age equal to 10.1 is fitted to the cluster. The main sequence turnoff is at a lower magnitude as compared to that of an open cluster. After reddening and extinction corrections, the distance to the cluster is found to be 1950 plus minus 192 parsecs, and its age is 12.6 billion years. This table gives the results obtained for each cluster. The figures shown in blue are from the Milky Way star clusters catalog included for comparison. For NGC 1960, the results of a recent paper, Photometric, Kinematic and Variability Study in the Young Open Cluster NGC 1960 by Y.C. Joshi et al. Are also included. Some of the things that I would like to explore further would be the use of code to do the entire analysis, apply reddening correction to each individual star instead of using a single averaged value, the appropriate treatment of negative parallaxes, and possibly treat this as an inference problem and use the Bayesian approach. These are the references that I have used. I wish to acknowledge the following: Gaia Collaboration and Archive, Topcat by Mark Taylor, Padova Isochrones, Astronomy from Archival Data, the IAU OAD project, and last but not the least, Dr. Priya Hassan and Dr. Najam Hassan for providing this wonderful opportunity to explore the fascinating universe with them and my colleagues in the course. Thank you.